In this video, we will do a subset proof using the definition of a subset. So recall that we say S is a subset of T. What that means is for all elements X that are in S, that are in the first set, X has to be in T. X has to be in the second set. Okay, so let's do an example. Let's let A be a subset of B, and I want to confirm that A union B is a subset of B. And I want to first do this by drawing a Venn diagram of each side. Okay, so ordinarily, if I had a union, I would have a circle for A and a circle for B. But in this problem, it tells me something about A and B. It tells me that A is a subset of B. So the circle for A is within the circle for B. So I'm going to draw that within my universal rectangle. And let's draw one more version of this. I'll copy it. Let's put another one of these because I'm going to draw a Venn diagram for each side, for the left-hand side and for the right-hand side. So for the left-hand side, I need A union B, which means that's everything that's in A or in B, all of it gets shaded. So not only does everything in A get shaded, but everything in B also gets shaded. Everything in B also gets shaded. Okay, so on the left-hand side, I've shaded in everything in the union. All the blue stuff, all the green stuff is in the union. Now for the right-hand side, it says shade in B. So I'll put this in a different color. If I just shade in B, we're shading in that circle. And if I compare my two Venn diagrams, well, we've shaded in the exact same thing. For both of them, it's actually just the circle B. So it actually looks like these two sets are actually going to be equal. In this problem, we're just going to prove a milder, like an easier version of that. We're not going to show that they're actually equal. We're just going to show that the left side is a subset of the right. Okay, so visually in these diagrams, it does seem like that's the case. The left-hand side does seem to be a subset of the right, because in fact, they look like they're equal. Now, let's prove it using the definition of our subset. So to do this, I'm going to do scratch work. So I'm going to make a column for what it is that I know, what it is that I want to show, which I'll call WTS. So what is it that I know? Well, the problem tells me that A is a subset of B, so I'll write that. A is a subset of B. And because I want to prove the left-hand side is a subset of the right-hand side here, the way we do that using the definition is I first take an arbitrary element, I call it X, of the set on the left. So for my problem, that's A union B. So I'm going to let X be an element of A union B, of the left-hand side. And what I want to show, bullet point, is that X is an element of the right-hand side, which is B. That's my end goal. Well, so how do I do that? Well, if X is in the union, what that means is X is either in A or X is in B. Okay, and well, in the second situation, if X is in B, well, I got what I want, and we'd be done. Well, if X is in A, how do we get to saying X is in B? This is where I have to use some of my given information. I know A is a subset of B, so if I know I have something in the smaller circle A, well, it's got to be in the bigger circle B, because A is a subset of B. So if X is an element of A, this automatically means that X is in B, because A is a subset of B. Okay, so since A is a subset of B, that'll be my reasoning. Oh, but that connects me to what it is that I want to show. So in both of these possibilities, we get that X is in B. Okay, so we got the scratch work. Now we are ready to write up our formal proof. So I start off by writing down what it is that I get to assume is true. So because I'm trying to prove the left-hand side is a subset of the right, I'm going to start off by saying, let X be an arbitrary element of the left-hand side of the union. So of A union B. That's something that I get to assume is true. And I'm hoping to show that X ends up being an element of B. That'll be my last step if I can get to that. Okay, so I know this is true. I get to assume this is true. Let's break down what that means using the definition of a union. So then this means X is in A or X is in B. That's the definition of a union. Okay, so this gives us two cases. Two cases. Case one is, well, x could be an A. So I'll have to think about, well, what happens if x is an A? I'll put a comma there. And then case two is going to be, well, x could be in B. So if x is in B, we'll have to think about that case as well. Well, if x is in B, then we have exactly what we want. Okay, so I could just say if x is in B, we are done. We are done, because that's exactly what I want. We got x's in B. Awesome. So I love that. Sometimes that'll happen when we do a proof where we will literally have what we want, especially when we're doing cases like this. And that's awesome. In this first case, that's where we got to do a little bit of work. But this is where my scratch work helps me. Because if x is an A, the fact that I know A is a subset of B means that x has to be in the second set as well. So then I can say, then since A is a subset of B, this implies, so let me give myself more room here. This implies x is in B. So in both of these cases, we have what we want. X is in B here in the case one. In the case two, that's what we're assuming, x is in B. Therefore, I'll write my symbol for therefore, these three dots. Therefore, x is indeed in B. It happened in both of the cases, so it's definitely true. And that's what I needed. I started off by saying x is an element of the first set. I reached the conclusion that x is an element of the second set, but that's what it means. So that's what it means to say the first set, which is my union, is indeed a subset of B. So that completes the proof. So I'll write my symbol for done with proof. What I want to end this video by briefly talking about is, well, what are the ways to show two sets are equal? So in this problem, I showed one set is a subset of the other. It turns out that if you show both directions, that A is a subset of B and vice versa, that B is a subset of A, then they're actually equal. And we'll actually use this method most. So we'll mostly use this. We'll mostly use this in problems that we do. The other way we can show two sets are equal is to use the set identities that we talked about in the last video, the set identities in this table.